Welcome back. This is part 2 of the lecture on linear independence. And as you may remember, we were in the process of providing a definition for a relation of linear dependence and the definition of a trivial type of such relation, a trivial relation of linear dependence, and therefore that allows us to step in and classify sets of vectors as independent versus dependent. And formally they are called linearly dependent or linearly independent. The key in the classification of linear independence will be whether or not we can find or determine if there is a non-trivial relation of linear dependence. In other words, whether or not we can establish that it's possible to find scalars, not all of them equal to 0. And in such case, if there is a non-trivial relation of linear dependence, then we would say, yeah, indeed, this is the case of a linearly dependent set. That should also be contrasted with cases that we discussed before. Specifically, we were motivating this with an example in which one of the vectors was expressed in terms of the other vectors, and then we did this repeatedly. We did this 2 times, and we're able to come up with a smaller subset. And so that the idea of having vectors that are in fact expressed just like dependent variables in terms of free variables, there are vectors that can be expressed as a linear combination, non-trivial linear combination of the other vectors. And that's precisely what takes place when a set of vectors is linearly dependent. Specifically in this example, the original set of vectors, here these vectors W1, W2, W3, W4, this would be an example of a set that is linearly dependent because there is a non-trivial relation, meaning that there are scalars here, alpha 1 equals 2, alpha 2 equals 3, alpha 3 equals 0, and then alpha 4 equals 1. Right? So this is a set of values for the scalars, is a non-trivial set because at least one of them is 0, but not all of them are 0. And then that leads to satisfying the definition of linear dependence. Very well. So we have established and reviewed the definition for a set being dependent. And if the set is not dependent, it's classified as independent. And the idea of independence is there is no way of expressing that linear combination equal to 0 vector with other coefficients different than the 0 values. So for the set to be independent, the only combination, the only set of values for the scalars are when all of them are equal to 0. So now that we have these definitions, we can make use of some machinery we have developed so far, and this machinery is in terms of computing solutions for systems of linear equations. So let's consider this set of vectors. Each vector here is a member of C5. It has 5 locations, 5 entries, and there are 4 vectors. And we want to determine what are the possible values of scalars. So we want to consider this relation of linear dependence. This is a vector. This is a vector equation that is set to 0, but is set to this 0 vector. So if we wanted to be more precise, right, we could think of this right-hand side is really the vector of zeros in C5. So it has 1, 2, 3, 4, 5 zeros, right? So that's what we mean with when we write this. And in the question of addressing dependence is we want to classify this vector, determine if it's dependent or independent. So we need to know what are the values of the scalars. So we're looking for what is alpha 1, what is the value of alpha 2, what is the value of alpha 3, the value of alpha 4, right? And so this type of calculation is no other thing than solving a system of linear equations. So as we formulate this as a homogeneous system of equations, first we note that because this is something in the spirit of homogeneous system of equations, the trivial solution always does the trick. If you let the scalars all be zero, indeed this will be satisfied, but is it possible for other non-trivial solutions to exist? So thinking as a homogeneous system of equations, we store each of these column vectors in the matrix such that each of those column vectors is the column of this matrix. We think of this as the matrix of coefficients, the matrix of coefficients of a homogeneous system, and then we go ahead and row reduce, right? So in this case, there are 4 columns. So we're looking for potential values for scalars, right, or for variables, and we find that R here is equal to 3. So there are rows of, in fact, there are 2 rows of zeros, but importantly, n minus R equals to 1 in this case. So we would say, from all this type of calculations, the way we're carrying this out, we say 1, 2, and 3 are indices of dependent variables, thinking of the alpha values as variables. And this is not an augmented matrix, right? So this is the matrix of coefficients. So the index 4 denotes an index of the free variables. So here we would say alpha 4 is going to be considered a free variable. And if we set the information we gain from here, so given that alpha 4 is considered here the free variable, then the RREF would tell us, remember, we're thinking of this as a homogeneous system, so we set this equal to 0, and so we would have 1 alpha 1 plus 0 alpha 2 plus 0 alpha 3 minus 2 alpha 4 equals 0, and so therefore we can solve for alpha 1 in terms of alpha 4. We find also another expression for alpha 2, and the third row there would tell us, this row would imply that alpha 3 minus 3 alpha 4 equals 0 implies that alpha 3 equals 3 alpha 4. So it's possible to set all the scalars in terms of the free variable here, alpha 4, and if we set one specific value for alpha 4, then that would give us a set of values. So suppose that alpha 4 equals 1. So if alpha 4 is, if we say this, let's let alpha 4 be 1, then this, in terms of values for alphas, this would give us alpha 1 to be 2, alpha 2 to be minus 4, alpha 3 to be 3, and alpha 4 to be 1. Which is exactly what we consider here. So let's suppose that we set alpha 4 to be equal to 1, and so this gives us a set of values that are now considered the scalars on this linear combination. Each of these is uses a scalar here, and so on. And so this will be a non-trivial relation of linear dependence, and therefore we would say that that set composed or made of these columns is a linearly dependent set. Now, this theorem called linearly independent vectors and homogeneous systems, trying to bring together again solution sets in the context of relations of linear dependence. So this is stating, consider the homogeneous system that has the matrix A as a matrix of coefficients, and now name the columns of that matrix of coefficients A sub 1, A sub 2, A sub 3, all the way through A sub n. So A is assumed to have n columns. This is true, okay? This is true even when A would be rectangular, right? This could be, in general, the matrix A has m rows and n columns. So this is a case in which there are more rows than columns, but we could also have a rectangle in this form. This would be a matrix A. It has m rows and n columns. So n always denoting here the number of columns, and regardless of how many, whether it is rectangular or square, we're assuming that each of these columns is an element of Cm. So each column would have m entries, right? So whether it is a short column or rather a long column, each column is a member of Cm. Then we classify the set made of the columns of the coefficient matrix. We classify that set as linearly independent if and only if the solution set of this homogeneous system has the trivial solution as the only element, has a unique solution being the trivial solution. And so this theorem is rather a useful tool because this will rely on computing the reduced row echelon form. Suppose we consider this set. There are 3 columns. Each of them will be considered the columns of a matrix of coefficients in a problem homogeneous system. First column is called A1, second column is called A sub 2, third column is called A sub 3, and now what we do is we proceed as if we were computing the solutions of as if we were computing the solution set of this linear system with matrix of coefficients A and 0 as the vector of constants. And immediately what this RREF is telling us, so in this case we just argue here that this matrix row reduces to this matrix, this RREF, and this is not an augmented matrix, so it's not a problem to have 1 over there. This is the matrix of coefficients row reducing to this matrix, and this implies that indeed x1 equals 0, x2 equals 0, and x3 equals 0, being that in this case the number of columns of the matrix is 3, the number of non-zero rows in the RREF is also 3, and so here n minus r, they match each other, and we find that the only solution here is the trivial solution. But that fact that the only solution of this homogeneous system is the trivial solution is what implies that we have linear independence. So the set that we were trying to classify, that set of columns, of column vectors, that set is linearly independent because when we form the matrix that stores those columns as the columns of this matrix, and when we row reduce, we come up with a conclusion that the only solution of a linear system that has that matrix as a matrix of coefficients, the only solution is the trivial solution. In other words, I was calling these x's here, but this would be the alpha values. This would be alpha 1, alpha 2, and alpha 3. The only way to have the relation of linear dependence be true, be satisfied, is by choosing scalar values that are all equal to 0 at the same time. And that is an implication that establishes that this set is linearly independent.